Alright, so hi you guys. In this section I'll be explaining to you polynomial functions and how to really understand them and how to analyze their graphs and a bunch of other stuff. But before we get to 3.2, which is what this section is, I wanted to introduce you to a specific notation. Is where you see an x, an arrow, and then infinity sign. This right here means that x approaches infinity or goes to infinity. By that I mean that it doesn't equal infinity, because you can't really equal infinity. It's obviously infinitely many numbers, but it's the behavior of the value of x as we approach infinity. Make sense? So if I write it like this, this means it's x goes to infinity. If I write it like this obviously means x goes to negative infinity, right? And if I write it like this, by that I mean that f of x is what's going to infinity, and by f of x I obviously mean y, because these two are the same thing, if you guys remember, right? And if I write it like this, I obviously mean that f of x is going to negative infinity. So when I say that one of these goes to negative infinity, what I mean is value-wise. Like if you look at the coordinate system, any graph you might draw on this starts at the point 0, 0, heads either right, left, up, or down, depending on the value you want to plot, right? Well, the idea here is if you're observing x, I want you to look at the x-axis and see how the x values behave. So when I say x is going to infinity, I mean that the x values on the x-axis are going towards the positive infinity end. Make sense? And if I'm saying that x is going to negative infinity, that means it's going towards the negative infinity end. Same thing for f of x. And like I said, f of x really represents y. So the y values, so the vertical y-axis, is what you're going to be looking at. So how does the function, whatever is plotted where the points are, how it behaves as y itself goes to infinity or negative infinity. So I hope that made sense. Now, before we keep going, I want to show you the generic form of a polynomial function, which I believe I already have in class before, but since in this section we'll be talking about polynomials again, I want to remind you of what it looks like. So this is a way to write down or to include every single polynomial possibly written in one form, which is why it looks kind of scary, but don't be scared by it. So the first term is a subset n, right? So an times x to the power of n plus a n minus 1, x n minus 1, plus dot 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 a1 x to the 1 power, which is why it's not there, plus a 0, right? So again, we looked at this before, and if you compare it to any normal polynomial, like 3x squared minus 2x plus 1, you can see that the power, which is what these two indicate, the power reduces by 1 as you go on, and it is multiplied by a coefficient that could sometimes be positive, could sometimes be negative, and it could be 0. And if it's 0, it's going to disappear. So in this case, in the case of the example I wrote here, the power of this polynomial is obviously second, and then goes to first, and then goes to the number, which is what you see right here, tail end. If I gave you something to the 7th power, then it would be 7th power, 3rd power, 7th power, 6th power, 5th, 4th, 3rd, 2nd, 1st, and then 0 power. Make sense? So this is the form of a polynomial number. Now, I want you to note this right here, a to the n. A to the n here is the coefficient of the leading term. So the leading term would be the x with the highest degree, right? The first one. So sometimes I could give you a polynomial with the terms kind of jumbled, right? Missed, either not in order. So in that case, you need to be careful, because it's not the first coefficient you see, it's the coefficient of the highest degree, the degree of the function. That's the one you want. So an. Now, the behavior, what an is, represents how the function would generally look at the tail end of what the function is, and it also tells you if it's going to be pointing up or down. Now, there are two cases, and for each case there are two scenarios, so 4 total, right? For the first one is if an x to the n was even, where n is even. Yes? So that looks like Nevin, but or never, maybe I should do this. Anyway, so I'm basically saying that n is even. There, that's a little better. So in the case where n, which I mean the power, and the number over here is subset, that doesn't really affect what the value of this number is. It's just something that we use to note, but it does affect the function itself. So basically I'm telling you that the polynomial has an even power. The highest power is an even power. So if that is the case, you have two case scenarios. The first is when an itself is positive, and the other one is where an is negative. Right? So if it's positive, what happens? If it's positive, because the function we're considering is an even function and a is positive, that means that the ends of the function are both going to be pointing up, like a parabola or a function to the 4th degree. Right? Both ends are going to be pointing up. Now, if it's negative, then both ends are going to be pointing down. Oops. Actually, it's this. Ignore that one, that's not there. Alright? So, when it's even, note that both ends are always together, either both up or both down. Both up, both down. Now, positive is up, negative is down. So far so good? Now let's go to the second case, which is where an is multiplied times x to the n, but n in this case is odd. By this, I mean that the function you're considering, it has an odd power. So the highest power would be 3 or 7 or 13 and so on. Yes? So for this one, you also have two cases. One where an is positive, and the other where an is negative. Right? So for the first one, when an is positive, because this is an odd number, that means, odd power, that means the function is going to have mismatched ends, right? For this one, let's call them matched ends, and for that one, let's call them mismatched ends, because for this one, for the even functions, both ends behave in the same way. They're either both up or both down. For the odd function, it's going to be one up, one down, and for the negative, it's going to be the same way, just the opposite direction. So it's either going to be right one up, left one down, or left one up, right one down. So if I draw like the graph of a cubic function, it would look like this. This is a positive function, and this is a negative function. I thought, okay, so for the even we said positive, both up, that's easy to tell, negative, both down. But how can I tell the difference between the positive and negative for the odd function? Well, that's easy. You need to consider how the function looks on an axis, right? So if you were to graph this, you need to look at the values of x. I'm saying right here that as x is positive and it's multiplied times xn, that means I'm saying that the function itself is going to behave in a positive way, which means that the okay. Let's do question number 1 on your note set. Alright, so the question says, use the leading term to define the end behavior of the graph of the function, but without actually seeing the graph of the function. So here's your first one. F of x equals x to the 5th minus 5x to the third plus 4x. Yeah? So this is my polynomial. This is what I'm trying to find the end behavior of without actually having a graph. So what you do, you grab the leading term, make sure it's the highest power, which it is, and then what do? You write down here, and you go, okay, so I have x to the fifth, no coefficient or seemingly no coefficient. That means the coefficient is simply 1, right? And there's no sign, so it's positive. So it's a positive 1. Now the power is odd. That tells you what? That the ends of the graph are going to be pointed in different directions. They're not going to be matched. So it's either one up, one down, on the left side or the right side. It depends on the sign. Okay, well my coefficient is, as we noted, positive. That means that the right one is going to go up and the left one is going to go down. Now I don't expect you to know what the graph of the function is supposed to look like, so I don't need you to scribble what this should look like, but you should just tell me that the end behaviors behave in this manner. So I would just draw the axes like this and then tell me that on the right side is gonna go up, and write the word up if you want, and on the left side is gonna go down. So far so good? Let's do one more. Here's another example. How about g of x? And I'm saying this time that g of x is actually negative 2 multiplied by x minus 5, which is multiplied by x plus 1 to the third power. Well, that looks like a mess. Well, don't be scared. You know how I usually show you guys quadratics or cubic functions and we factor and it's a pain? Well, on this one, I kind of made it easier on you and factored it for you. This is just simply a factored form of a polynomial. If you multiply all of these together, it should give you a polynomial to a certain degree. Can you tell me which one? I'm going to pause a few seconds so you can pause the video and think. But the answer would be to the fourth. And how can I tell that? It's because the number of x's you multiply is what indicates the power of the function. Now over here we have a pair with an x, so that's 1, right? We have another pair with another x, that's 2 x's. But the thing is, this one has a power of 3. That means you have this pair 3 times. So how many pairs of parentheses do we have total? 4, which means how many zeros are we going to have? 4. And like I said, the degree of the function usually matches the zeros. So since they're 4, that means you're going to have the power, the highest power is going to be the fourth power. Make sense? So the power here would be x to the fourth. So far so good? Now, notice that inside the parentheses, we have no coefficients. That means at least the very first number where you multiply every single x you see is going to be x to the fourth with no coefficient, right? Wrong, because after we did all of this, that part is still true. It's just that you missed the negative 2 over here. We have a negative 2 multiplied times all of these parentheses. So after you're done figuring out that it's actually x to the fourth, you need to make sure that you don't have any other multiplications outside, which we do in this case. It's a negative 2. So the answer is actually negative 2x to the fourth power. So this is what we're considering now. Again, look at the power. It's even. 4 is even. What does that tell you? That tells me that it's going to be matching. The ends of the function are going to match. They're either going to both go up or down. Now, the fact that it's multiplied by a negative means they're going to go down. So you could say that both ends of the function are going to be going down. This is enough. That's all you need to do. Just draw an arrow and tell me how it behaves at that end. If you feel like you want to write down the axes, you can. It won't always be like this. Sometimes it could be on this half, but it's still pointing down. But this is just a rough sketch just to help you understand the concept, and drawing out the axis shouldn't really affect your answer. Okay? So the answer I'm looking for is the arrow itself and the word down, not the graph. Alright? going to learn a new trick. That was the learning the end behavior of the function by looking at the coefficient and the power of the leading term. Well, now I want you to be able to identify the zeros and their multiplicity. So when I say zeros, I don't mean the number 0. I mean the values of x in that function that will give you that result out of the function. So basically the solutions. If I gave you a polynomial and asked you to find x, you would factor or use the quadratic formula if it's quadratic, and you will give me the answer, and the number of x's that function is going to have is going to match the degree of the function, right? So those answers you just found, those are called the zeros of the function, because when you solve for it, you set the function equal to 0. Make sense? So quick example. F of x is what? Let's see. X to the third minus 5x squared minus 16x plus 80. Alright, so for this example, you have a polynomial to what degree? It's the third degree, and what I need you to do is give me the zeros of this function. So in order to do that, all you have to do is basically set the function itself equal to 0, hence the name, and solve for x. That's all you need to do. So as a note here, just so you'd have it in your notes, set it equal to 0 and solve for x. Yeah? Finding zeros. I hope that helps. Alright, so after you set it equal to 0, now we solve this, and easiest way, since this is a cubic, is to factor. So let's do that. Alright, so let's try to spot patterns here. The 16 and the 80 have a number in common, so we could probably factor a number out of there. Over here, however, you have 5x squared that is negative, and an x, so if I want to factor something out, it would probably be x squared. So if I factor x squared out of the first two terms only, I'm only playing with the first two terms. If I take x squared out of the first two terms, 2 divided by x squared gives you x. Negative 5x squared divided by x squared is going to give you negative 5. Yes? So now it's x squared times x minus 5 minus 16x plus 80, because I didn't touch that part and it didn't go away on its own, so it stays there. Yeah? Now, I'm just copying the first part, and I want to focus on this one right now. So if I do that, over here, let's look at it. You have 16x plus 80. Now, if I factor 16, because you can obviously see there's something in common between these two numbers, since they're both even, you at least have 2. And since 16 is a multiple of 8, so you can obviously take out an 8 out of there for both. But if you do the division, you can use your calculator if you want. 16 actually does factor 80, and the answer is 5. So if I factor out negative 16, and please note the sign, it's already negative over here, but if I factor out the negative, I'm dividing both terms by negative. Alright, so if it's negative 16 gets taken out, that means I'm multiplying both of them by negative 16. That means I'm going to divide this one by that negative 16, and you end up with the x, which makes sense. I just took out the negative 16. And the positive 80 divided by negative 16 turns it negative. So the answer is negative 5, and it equals 0. So if you can see where I'm going with this, now I have subtraction between two terms, only two terms, with a multiplication between them. So I can factor out this pair. So I want you to look at this pair of parentheses as one unit. One unit that I'm going to factor out. So you take it, you divide both terms by it. So x squared times this divided by that pair gives you the x squared minus 16 multiplied by that pair divided by that pair gives you the 16. Alright, and with this I factored out the first pair out of the 3, because again, this is the third power. That means you're going to have 3 solutions. So this is the first one. X minus 5 is just the first pair. Now this one could be factored, but this one's a lot easier. So the answer would be x minus 5, still as is. Now let's factor this one real quick. And as you can see, we have no terms in the middle. We don't have an x. It's just a squared and a 16. So that, that should tell you that they're going to be almost the same. It's just that you flip the sign. So for this one, since it's a 16, obviously it's going to be 4 and 4. And since it's negative, 1 positive, 1 negative, and that's why the middles cancel. And that's it. We just factored it. So to solve, you set each one equal to 0, like we know. We've done it this 100 times. So x minus 5 equals 0, or x minus 4 equals 0, or x plus 4 equals 0, right? Grab it, move it. And when you do, you flip the sign. So x is 5, or x is positive 4, or x equals, can you guess? Negative 4, because again, we move it and the sign changes. And those are your 4 answers. Now, if while you're watching this, you're trying to solve it along with me, and you did this a little different, you solved that one separately because it's always going to be the same, but instead of factoring this one out, you went, well, I could just do this, x squared minus 16 equals 0, and then move the 16 to the side. So x squared now equals positive 16, take the root, and x equals 4. You're right, that's also an acceptable answer. You arrived at the same conclusion anyway. There are so many ways you can solve a math problem. As long as you get the right answer, I don't care how you do it. Now, but doing it this way, you need to be careful, because taking out the root, you need to remind yourself every time to add the plus or minus. Because any number, once you square it, you get rid of the sign. So it could have possibly been negative 4 squared, and that gave you that 16. So when you take a root of something that's been squared, you need to account for both positive and negative possibilities. So if you do it this way, you need to remind yourself of that, otherwise you're going to miss an answer. But if you do it this way, you will receive both answers regardless. Make sense? So these are the zeros. Now, so what if I show you a different one? Now, here's another question that says, determine the zeros and their multiplicities for this function. And in this one, instead of asking you to factor, I'm just going to give you a function that's already been factored. Alright? So, let's go with 4. This function of x is 8x multiplied by x minus 1 squared times x plus 3 cubed. Alright? Now, had I given you the original function, it would have been a function to what degree? Let's count. You have a 3, you have a 2, that's what, 5, and the 1, 6, right? So this is a function to this degree. Again, what I'm counting isn't how many x's you're seeing, it's the x's and the powers they have, because basically that means I have 1 8x, I have x minus 1, the pair, twice, and x plus 3 times. So that's a total of 6. You basically add, this is a 1, this is a 2, this is a 3, you add the powers, and that gives you a 6. Okay? But this only works when they're multiplied. So it has to be factored. You don't go to a normal polynomial with a bunch of terms added together and you go, okay, so I'm adding these. No, that's already done. You just look at the leading term. You only do this when it's factored. Okay? Now, so this is the 6th degree. So knowing that, how's that going to help me? The question is asking you to find the zeros, right? Well, since this is already factored, you don't need to do what we did up there. You just need to solve each one as though it equals 0. So considering the 8x, if you have a number multiplied by x and it equals 0, x automatically is 0, because anything multiplied by 0 is still 0, and if the answer is 0, that means x itself is 0. And if you still need to see it solved, all you have to do is basically just divide by 8 on both sides. On this one it cancels, you get x, and 0 over 8 is still 0. Make sense? So anything multiplied by x and x alone. Yeah? So I want to stress that it has to be x alone, so not x minus or plus a number, because that removes the 0. That eliminates the possibility of a 0. If it's just x, like this, and you multiply by a number, the answer is always going to be 0, no matter what the number is. Alright? So if you have x multiplied by itself, that's always going to be 0. Now over here, when you see a pair of parentheses like this, I want you to spot the pattern that every time the answer for that x is basically going to be the number right next to it. And I want you to flip the sign, because I want you to picture it like over here you have x minus 1 equals 0, right? So when I'm solving for the x, I'm moving the one to that side. So every time you look at this, flip the sign in your head and you go, okay, so x actually equals positive 1, not negative 1. You notice that? So if it's a pair of parentheses with x and a number subtracted from it, you know the answer is going to be positive. And this one is going to be the opposite. Since it's added to it, the answer is going to be negative. But again, if you can't see it, or you feel better if you just solve it by hand, go ahead and do that. And x is going to be a negative 3. So far so good? Alright, so now we go back to the lesson. We're talking about multiplicities here. So what do I mean by that? I mean how many times that 0 is multiplied by itself. So over here, which basically means the power. Because this right here, like I said, having x minus 1 twice, that means you have that pair of parentheses twice. And having this one 3 times, that to the power of 3, that means you have this pair of parentheses 3 times, right? So that's the multiplicity I'm talking about. So all you have to do when you come to this part, after you tell me what the zeros are, so you need to do this. So after you tell me what the zeros are, underneath each one you tell me this one has the multiplicity of, for example, for this one it's just 1, because it was to the first power. For this one, it has the multiplicity of 2, because it was to the second power. And this one has a multiplicity of 3, because it had the third power. Make sense? That's it. Just tell me what the 0 is and how many times it repeats. Right? So that's the zeros and their multiplicities. Alright? And the reason we didn't do this in the first one, if you're wondering, is because each one only happened once. But on a test, please do. Like if I give you a question like this and ask you what are the multiplicities after you're done factoring it, or if I'm nice enough to give it to you factored, then all you have to do is tell me what the zeros are and their multiplicities. So in this case, it's the multiplicity of 1, multiplicity of 1, multiplicity of 1. Yeah? Alright. Let's keep on. Alright. So, now that we know that, I want to introduce you guys to a concept of what the multiplicities really mean, right? The power of that multiplicity has a meaning when it comes to the function itself. So bear with me. Here is a function, g of x, and it is x times x minus 1 times x plus 3. Alright, so I gave you the factored form. We have 3 items multiplied together, so you know that that's at least going to be to the third power. And since each is 1, that means we have the multiplicity of 1 for this one, 1 for that one, 1 for that one. So really it's only the 3 answers you see. And if I want to graph this, it would look, yeah, it would look like this. So we said this one's always going to be 0. So this x is 0. That means we have a point at 0. Over here we said that the negative means what? That the answer is actually going to be positive, and it's always the number you see. So it's going to be positive 1. So I'm going to go to positive 1. And over here is going to be negative 3 at x. Now, why am I putting those points on the x-axis? It's because these points are your zeros, and by 0 I mean it's the point where the function equals 0. That means that your x intercepts. Do you remember when we said that if you're finding the x-intercept, that means you're setting y to equal 0, which means the function itself is 0. So when you solve for the zeros, you're initially finding your x-intercepts. So the x values here are going to be the same values you have on your x-intercepts. And whenever you want to plot your x-intercept, what do? After you find the x values, for y you always plug in 0. That's why the points are always going to be on the x-axis, which kind of makes sense since they have to intersect the x-axis. Yeah? So, if I want to graph this function, which is a function to the third degree, it's doing this. Yeah? This is your cubic function. Now, notice three x's multiplied together. The coefficient on the outside, there's no number, and so that means it's 1, and it's positive, so there's no sign. And on this side going up, that one going down, right? Now, here's what I want you guys to look at. The points I plotted. Now look here. At the point x equals 1, or 1, 0, if you will, the function, as you can see, does what? It crosses, right? You have a few negative values right here, right? Negative, 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 all the way to this point, and then goes positive, right? So at this area right here, the function what? It crosses the x-axis, right? Now I want you to note that it's going to cross every time the power of that 0, or the multiplicity of that 0, is odd. So over here, x minus 1 had a power of 1. So it crosses the x-axis because x equals 1 has a multiplicity of 1. And I'm going to write the word odd between parentheses. Okay? Because it's 1, it crosses the x-axis because it's odd. That's the idea. It's either odd or even. So at x plus 3, which means it's x negative 3, right? This point right here. X plus negative 3. That point. So at x negative 3, or the point negative 3, 0, depends on how you want to look at it. For this one, the power is also 1, which means it's also odd, and that's why, as you can see, it touches the x-axis still. Same for the 0. It has a power of 1, so it's crossing the x-axis. Well, I think I said touch before. It crosses the x-axis here too. They all cross because they're all odd. They all have odd powers. So far so good? So as you can guess by now, if they have even power, they're going to behave differently. So let me show an example where they might have an even power. All right? I'm going to use the exact same function. I'm going to graph it again, but I'm going to change the power of the multiplicity of the zeros. So it's x minus 1, and x plus 3, right? But for this one, I'm turning the x minus 1 to a second power. All right? So this is 1, that's a 1, but the one in the middle is 2. Okay, so let's graph it. This changes the degree of the function, by the way. So because for this one, now we have a degree to what power? 1, 2, let me say 3, and then 4, right? You're adding. So it's power 4 now. So let's do that. Here is x-axis, and here's the y-axis. I think I need to be that long. Yeah. Alright, so we start here, and you go to the point x equals negative 1, which that means it's x equals 1, this is x equals 0, and that's equals x equals negative 3. We did those already. Yeah? So, at this point, x equals 1, or the point 1, 0, the function is going to approach, right? Do this, but it's not going to cross. It's not gonna go into the negative. It's going to just touch the x-axis and then curve up again. Go to the 0, and touch it like that. You see that? So it didn't cross it, it touched it, just touch it. Now, for the 0, it's an odd power, so for this one we do cross. So it does cross on that point. And it's going to go all the way down like this, and then going back up, and then crossing the x-axis again at the point x equals -3. This is 0, and that's 1. Right? So let's observe the points. Again, over here, what did it do? It crossed. It crossed it. At the point 0, it crossed because it had the power of 1. At the point +1, it touched it because it's an even power. So it touched the x-axis because it had an even power, or I should say power, or multiplicity. Alright? And at this point, as you can see, it obviously crosses, so it goes through because it's an odd power. Alright, so say it with me. Crossed is odd, touch is even. Cross is odd, touch is even. So when you see even, you think touch, and when you see cross, when you see odd, you think cross. Okay? Now, what about this example? Actually, before I move on, I think I might have gone through that one quickly. I know I repeated it a few times, but just to make sure you guys are not like running after me in the video trying to capture the frame, I'm gonna pause for 2 seconds so you can pause the video and copy this down if you need to. So this is the first one. And this is the second one. And while we're at it, just to remind myself to do it, I'll do it now. These are the previous set of notes I did just now. Again, here's the first one in case you want to write down like this. There you go. You can see the whole thing. And this one. That's the bottom of the page. Okay. Now, let's continue. So, I want you guys to look at the example I'm about to give you and see if you can figure out the multiplicities of the zeros, and then tell me if the function at those points, at those x values, is going to touch or cross the x-axis. Okay, but we're going to do this without graphing. So after I write down what the function is, pause the video and see if you can figure that out. So you have -3x squared times x plus 4 times x minus 7 to the third power. So this is your function. Again, pause the video, think about it a little bit before we move on. Now, if you look at this function, obviously it's what? It's factored. That means your zeros are kind of clear to see. Again, if you can't tell, just grab them one at a time. Every value is multiplied. You grab every x that's multiplied. You grab them one at a time, you set them equal to 0, and you solve. So set this equal to 0, you get what? 0, because it's not added to anything. Like I said, when it's just an x, it's just a 0. Right? Over here, we have x plus 4, and we said the sign always flips. Therefore, whatever number you see here is the answer, and this sign is going to be the opposite. So it's going to be x equals -4. And over here, since it's a -7, that means x equals +7. Make sense? Now, the multiplicities is the number you see right here, the powers. So we have a 2, we have a 1, and we have a 3. So that means the total power of the function is 6. And at x equals 0, you have a multiplicity of 2, right? At x equals -4, you have a multiplicity of 1, and at x equals -7, or sorry, +7, you have a multiplicity of 3. Okay, so we did the zeros, we did the multiplicities. Now tell me if each point is going to touch or cross at that function. So at x0, the multiplicity 2, that makes it even, and we said even is touch, right? Over here, 1, the multiplicity is 1, and we said odd is going to be cross, and over here it's what? 3, which is also odd, therefore it also crosses the x-axis. Alright, so that was the touch and cross and the multiplicity of zeros and how to manipulate them. Now, one more trick. This is really helpful to know, and it's not always like in the textbook, so I'm not sure if the Recursion has it. But please write this down because it's really important, and it helps you tell the degree of the function by looking at the graph, and it helps you figure out what the function is kind of going to look like once you're trying to graph it. So it helps you in both ways. So this is a trick to help you figure out what the turning points are and how many you have. Yeah. So the idea here says that each polynomial has one less than the degree. It's one less. Let me do it like this. One less than, oops, than the degree of the function. Right? So we have one less than degree of the function. So what is it I'm talking about? One less than what? I'm talking about the number of turns. Right? I'm talking about the number of turns. A function has one less than the degree of the function. By this I mean, if you have a function that is to like the 3rd degree, right? That means the graph is going to have at most, please note this because it is possible for you to miss one, or have one less due to the power and how the multiplicity is. But if it's to the 3rd degree, that means you're going to have at most 2. If it's to the 2nd degree, that means you're going to have at most 1. If it's to the 5th degree, you're going to have at most 3. Oh, sorry, 4. I thought I put a 4 there. So if you're spotting the pattern, it's 1 less at most, but it's 1 less. So 2, 1, 4. And try to picture it with me. If you try to think of a linear function, which is a function to the 1st degree, what does the graph look like? It looks like a straight line, right? Could be diagonal, could be horizontal, but it's just a line, which means what? It means it has no turns whatsoever. 1st degree, 0 turns. Now picture a parabola. This is a function to the 2nd degree. How many turns do we have? 1. Here we go. 2nd degree, at most 1 turn. Okay, now picture the cubic function. It does this, no? How many turns do you have? It's 1, 2, right? 3rd degree, 2 turns. What about this one? What function is this? Let's count the turns. We have 1, 2, 3. That means it's to the 4th power. What about this one? How many turns do you have? 1, 2, 3, 4. That means it's to the 5th power. Make sense? So if I give you a function and ask you to graph it, looking at the degree, subtract 1 from the degree, and that's the number of turns you're going to have for the function. So that gives you an idea of what the function is supposed to look like. Also, if I give you a graph and ask you, okay, what's the degree of this function? Easy, just count the turns. You go 1, 2, 3, 4. Okay, so I have 4 turns, add 1, that makes this a 5th degree function. For this one, 1, 2, 3. Okay, I have 3 turns, that means this is a 4th degree function, and so on. Make sense? Alright. So now, let's use all of that, everything I showed you today, and a few of the things we learned before to graph a function from scratch. I'll give you an entire function. We're going to use these tricks to analyze certain aspect of the function and be able to graph it without using a table. Alright, so just to be clear, to be able to do this, you need to understand, one, how to use the leading term to determine the end behavior, which is the first thing we did learn. The second one, you need to know how to find the y-intercept, which we know how to do. 3, you need to know how to find the zeros of f and their multiplicities, right? We also know how to do that. You need to find the x-intercept, which is basically the zeros anyway, so if you know how to find the zeros, you're good. Now, plot the x and y intercepts and the end behavior of the function. Draw a sketch, and then if you find the axis of symmetry easy to apply, find it. And if you remember, if a function is even, it's symmetric to the y-axis, and if it's odd, it's symmetric to the origin, right? You remember that. And lastly, plot a point if it's greater level of accuracy, just to make sure you get the correct graph. Right? So the 7 steps I listed are actually in your notes, so you can read them along with me if you want, and they're there for you to study later on. But let's get to it. Here we go. So the question says sketch the function, and this is the function I'm giving you. F of x equals x minus 1 squared, x plus 3, and x minus 4. Alright, so let's start from the beginning. Shape. I want you to tell me the end behavior. So end behavior. So what do? I need to figure out the power of the function, right? So it's 2, 1, 1. That's the power of 4. Plus x to the 4th. Okay. Do they have anything else multiplied? Nothing. Each pair of parentheses has the coefficient of 1, and there's nothing multiplied in front or anything in between. Therefore, the coefficient of this is actually 1. So this is my leading term. Now, the power is even. That means both ends are going to be pointing in the same direction. And it's positive, so they're both going to be pointing up. So I'm just going to draw like this. 2 arrows pointing up for both of them. Okay? So that part's done. Now, how many turns? Oops. Turns. How many turns am I going to have? Okay, so we have what degree? 4th. So that means it's at most what? 3, right? 1 less. Done. That part is done too. Okay. What about intercepts? Let's start with the y. To find the y-intercept, we set x to be what? X needs to be 0, which basically means you're finding f of 0, right? You just plug 0 into the function. So let's do that. If this is 0, this ends up being 0 minus 1. There's negative 1 squared, that's positive 1, right? So over here we have 1 times, actually let me write it down instead of reading it to you. Okay, so, right? Negative 1 squared times 0 plus 3, so that's 3, times 0 minus 4, which is negative 4. So we have 4 and 3 multiplied together, that is 12, negative, and this one's positive, and it's a 1, so it doesn't matter. The answer is going to be a negative 12. If you stop here, you got the answer half right. Because remember, the intercept needs to be in the form of a point. So it's a point 0, negative 12, and x is 0 because obviously we plugged in 0. Yeah? So that's your y-intercept. Now let's find the x-intercept. So, now here's the thing. The x-intercept is actually your what? Your zeros. So by finding the x-intercept, you are finding your zeros, right? So let's do that. So for the x-intercept, f of x itself has to be 0. Yeah? And the nice thing about this function, let me go down a little bit. The nice thing about this function is that I gave you the function factored already. So you can easily find the zeros. We have x minus 1, you move it, and it's what? X equals positive 1. You just flip a sign, alright? And it has the multiplicity of what? 2. That's the first one. Second one. X plus 3 equals 0. You move it to that side, and x is negative 3, right? So this is my second one. And it has the multiplicity of 1. Last one, you have x minus 4 equals to 0. Move it to that side, and x is 4. Now again, you can easily figure these out just by looking at what the pair is and flipping the sign in here. But in case that was still confusing to you, I wanted to write it down. And for the last one, it's multiplicity of 1 also. Yeah? So after having figured these out, these values are the values of your x-intercept. All you have to do is write them in the form of a point, which I will do here on the side. So, first point would be 1 and 0. Second point would be negative 3 and 0. And last point would be 4 and 0. Again, y 0 for all of them because we plugged in 0 for the y. I hope that makes sense. Now at this point, one more thing. Do they touch or do they cross? This is why the multiplicity is useful. I need to figure out if these points touch the x-axis or cross it. So let's figure that out together. Over here we have what? 1, and it has a multiplicity of 2. That means it's going to touch it, right? Over here we have a multiplicity of 1. That means it's going to cross it. And over here we have a multiplicity of 1, which means it's going to cross it. Okay? So far so good? Alright, now we try to sketch this. Okay, so since I have all the points here, I'm gonna add my y-intercept over here as well. 0, negative 12, and then go up a little so we can see the graph and the points together as I graph it. Alright, if you're ready, let's go. First point, 1, 0. So let's call this 1 and put the 0 right here. So 1, 0. Next one is negative 3 and 0. It's 1, 2, 3. So this is negative 3 and 0. Next one is 4 and 0. So it's 2, 3, 4. Call this 4, 0. And then you have 0 and negative 12, which is why I made this line kind of long. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, oh, I need more, 11, and 12. So negative 12 and 0 is going to be on the y-axis all the way at the bottom right here. Yes? Now I've plotted my 4 points. Also, we need to know that there are how many terms? 4, and at the point x equals 1, the function is going to touch. So we go from here and we start from the top. Why do I start from the top? Because it's a function and what? It's an even function and it's pointing up, right? It's positive. So go from here. Yeah, it's going to cross and then curve back to go to the second one. Now at negative 1, we said we what? We have how many points? How many multiplicities for that 0? 2, right? So it's going to touch it. It's not going to cross it. It's going to go back down, right? And it's going to drop all the way to the y-intercept, like that. Okay? And it's actually going to keep going even more down, but then goes back up again, and it goes all the way to the last point we have before it keeps going up. So as you can see, we have both ends pointing up like we predicted. We have 1, 2, 3 turns, and the intercepts all marked, right? That's it, that's your function. Now, in order to make your graph look nicer and to figure out how it can behave in areas between the points, because like how would you know that it does this and not just that, right? So I recommend picking a point between these two. So for example, right here, if you pick that point and plot it, that should help you determine the behavior. Same thing goes for that one. So yeah, that's it. That was graphing the polynomials. I hope this was helpful, you guys, and I guess you'll hear me in another video.